welcome to the module. So, in last module we have seen different the blocks of a closed loop control system. So, we have discussed about error detector and what is the functionality of an error detector, and we have also seen how to implement an error detector using operational amplifier, and we have also discussed about signal conditioning unit and the sensor that we are using on the plant. Now, in today's class we will extend our other modules that are used in our closed loop control system. So, what we will do now is that we will discuss about heating circuit on the plant, and we will discuss about different types of controllers that we are planning to, or we are going to show demonstration on using an operational amplifier, their working. So, especially we will be discussing about the on off controller, proportional controller, and if time permits we will look into the proportional and integral controller. Now, in order to understand about the functionality of this controller, and in order to understand about the implementation of this controllers using operational amplifier, one thing is important, that how exactly this work, what is the role of this type of controllers in the system. So, as we have already seen in the theoretical session, their importance, their working, we will also briefly discuss about how exactly these functions, and we will see the implementation of these controllers using an operational amplifier. Right. Before going back to the controller, what we do is that we will discuss on how exactly we are using an plant circuit. See, the plant circuit need not to be the same circuit that what we are using in this demonstration or in this experiment. It can be of any other plant too. So, since our intention was to show demonstration, we have built up our own plant circuit using a transistor, and we are generating a temperature on the transistor. How exactly the temperature is being generated on the transistor, that we will discuss. And after understanding about the input parameter or input voltage or input value that is required for the heating circuit to heat, or since we are saying this particular plant is a heating circuit, what is the requirement in order to heat the plant, and what is the range that we have to give as an input signal, as an input to the heating system. As a result, it heats the system. So, in order to understand that, first we have to understand how exactly the circuit looks like. Now, when we look into our plant circuit, so this is the plant circuit that we are using in this module. So, basically what we are using is, we are using an operational amplifier. This is a major and important thing one has to understand. So, where you will be understanding about the role of an op amp when connected in a negative feedback fashion to our transistor here, and we are using a transistor. So, this transistor will generate a heat, that is because of the op amp. How exactly? So, when we recall what we have discussed in our previous module, similar to that, where we are using voltage controlled current source, this is also similar to that voltage controlled current source circuit itself. So, just to understand, just to realize, so if you recall, we are taking a transistor, our circuit, and here we have a resistance, and we are saying the resistance value is 0.1 ohm and wattage. This is very much important, the wattage is very much important. Here it is connected to supply VCC. So, as you know, this is an NPN transistor, NPN, and this is 2N3055. Why I have considered 2N3055? Because 2N3055 is a power transistor. Since in this application, in order to generate heat, one important parameter is power. Right? When you look into the data sheet, you will understand the amount of power it is dissipated, like the amount of heat it is dissipated entirely depends upon power dissipation factor, which you can get the value in our data sheet. And that means higher the power, higher the withstand capability of your transistor. Since it has to generate in heat, it has to withstand for somewhere around more than 5 amps of current, 3 to 5 amps of current. It depends upon what is the input voltage that you are applying to the system in this case. So, no matter what, the power is an important factor. So, if our transistor has to withstand for such a higher currents. So, that is the reason we have chosen 2N3055, which is a power transistor. And forget about how exactly it heats. first we will understand the working of this particular circuit. Now, if you clearly see the difference between the previous circuit and this circuit, we do not have this particular portion, we have taken only this portion. We will also take R2 resistor, which is of 180 ohms. So, this resistor is just simply 180 ohm resistor is simply a current limiting resistor. So, here we are applying some voltage. Now, what happens in this case? If I say this is V in, if I say this is V in, what happens? It looks similar to that of your transistor operating in a switch mode, isn't it? So, since the voltage across base and emitter is greater than 0. So, basically it should be greater than 0.7, that you can look into the data sheet what is your BE voltage drop. So, if you are applying more than that particular voltage, your transistor will be operated in a on condition, in a saturation mode, right. So, since it is operated in a saturation mode, it is nothing but a simple switch, right. So, I can rewrite the circuit in this fashion, since I am applying voltage greater than 0.7, isn't it? This will be VCC, this is 0.1 ohm. So, what happens when I observe the voltage drop across this resistor is nothing but your VCC, and the current flow, if I see, so I is equal to V by R, VCC divided by, since I am using 0.1 ohm. So, if I say 15 volts is my current and 0.1 ohm, so it will be 150 amps of current. Actually speaking, it has to pass 150 amps of current, but does your transistor withstand such a current? No. If you look into the data sheet, 2N3055 can withstand only a current of maximum 10 amps. Now, but how exactly it is heating? The reason why it is heating, because one important factor is power. So, that is nothing but what is the voltage drop across here transistor, and what is the current flow. Now, when you calculate the voltage drop, since it is in a saturation mode, and we already know that when the transistor is in a switch mode, the voltage drop across your collector and emitter is nothing but your 0.7 volts. That also you can refer in the data sheet, approximately somewhere around 0.7 volt. So, in this case, only because of your current, that means 150 into 0.7, because of your current this may heat, but when you understand, when you see the voltage drop across this point, this is simply VCC, right. But how do I control the current? So, in this case you do not have any option, even though whatever the voltage that I am applying above 0.7, it does not matter, the transistor will be always in a switch on condition. So, the voltage drop across this VCC will be always the voltage drop across this resistor will be always VCC. So, you cannot control the temperature, or you cannot control the flow of current or voltage drop across this particular circuit. So, we require, so since our intention was to control, the plant should have an ability to change the input, to change the output parameter based upon the input parameters. So, in this case output is temperature and input is some either current or voltage. So, if you can do such kind of a mechanism to system, right, even we can make use of the same system to control as per our requirement. So, how do we do that? So, with this case it is not possible. So, that is the reason we are using another operational amplifier, which is TL082. You can go with any other op amp. So, what we are doing is, rather than connecting this voltage, we are connecting here. Now, the complete working will change. How? If you recall, if you remember about operational amplifier basics, one thing is clear, that say two golden rules, if you remember. One is virtual ground concept. What does it mean? Whatever the input voltage that you apply at the positive, the same input voltage will be even at your negative. That means the voltage drop across the positive terminal and the negative terminal will always be same. So, if I say this is V plus and this is V minus, V plus is always equal to V minus, or V plus minus V minus is equal to 0. So, this is the golden rule, and another important thing is very high input impedance, so no current will flow through the system, that we already know. So, now in this case what will happen? In a previous case, when there is no this particular circuit, we have seen that the current flow here is entirely depends upon what is the resistor that we are connected here and what is the voltage source, and the voltage drop across is VCC. But in this case it will not be the same. The reason is we have connected the negative terminal of an op amp to the resistor point here, which is nothing but the emitter, right. This is base, this is collector, and this is emitter point. So, what happens? Since this is Vn, as per the property of your op amp, this also tries to maintain as Vn. As a result, it forces the voltage drop across the resistor to be of Vin, right. So, that means this is completely in a forced condition. The previous case is it is not a force, it is a free, meaning we do not have any influence of input parameter on the voltage drop across the resistor, but in this case because of the operational amplifier, it forces the drop across the resistor to be same as what is the input voltage that we are applying here. So, as a result, when we calculate the current flow through this particular resistor, so which is nothing but your IE, or which is nothing but the current flow through 0.1 ohm resistor, it is nothing but voltage drop across your resistor divided by resistance, right. So, what is voltage drop? Vin. So, Vin divided by 0.1, which is nothing but 10 times of your Vin. Now, what range of Vin that we have to use? That is also very much important. Now, if you understand, so if you understand the collector current in this case, when you see the collector current, the emitter current in this case entirely depends upon the input voltage and with a gain of 10. So, as if you recall the 2N3055, when you look into the 2N3055 data sheet, one thing we can clear that what is the maximum current it can operate at. So, when you see that it is somewhere around 10 amps. So, since it can operate only at 10 amps of current, more than that it will damage. So, the IE maximum value should be always 10. So, in order to achieve that, so the maximum range of Vin should be always 1. So, that we will get the IE current as 10 amps. Now, if I want to understand the relation between, Vn and IC, so since we know IE in this case, which is depend upon Vn, we can also convert into IC, as we know that IE is alpha times of IC, where IC is alpha times of IE, where alpha is nothing but somewhere around 0.99 into IE, right. So, IC value will be alpha times of 10 into Vn. So, which is, so if I know Vn, 0.99 into 10 into Vn is the relation between IC and Vn. But our intention was not about the relation between Vn and IC, we should understand how it is responsible to generate heat on the transistor, right. So, as we have seen, the responsible parameter in order to generate heat is power. Now, in this case what happens? Because of when I apply input as 0 volt, Vn will be 0. So, no current will flow through that. So, the transistor will be always at 0.7 volts. So, since no current, no voltage. Now, what if I apply 0.1 as Vn? Since this is 0.1, this will also be 0.1. If you understand the input voltage, let us say VCC is 15 volts and the voltage drop here is 0.1. What about the rest of the voltage drop? If I do not have the operational amplifier, we can see that the drop across this transistor is of 0.7 volts, and out of 15 remaining will be completely across your resistor, which is 14.3. But in this case if you see, the voltage drop across the resistor is 0.1 volts. So, that means 15 minus 0.1 is nothing but 14.9 volts. So, what is happening to 14.9 volts? As we know, energy neither be created nor destroyed. So, because of that, out of 15 we got only 0.1 volt here. So, remaining 14.9 volts will be the drop across the transistor. and because of this 0.1 volt, what will be the current flow? So, when we calculate, it is nothing but V by R 0.1 divided by 0.1, which is 1 amp. When you calculate the power dissipation factor, power across the transistor, it is nothing but V into I. So, voltage drop is 14.9 into I is 1 amp. So, that means somewhere around 14.9 watts is being generated, is utilized by your 2N3055. When you look into the data sheet, it gives you the power dissipation factor, which gives you the relation between the wattage and the temperature generation, right. So, based upon that, we can get a relation between the power and the degree. Now, if I increase the voltage to 0.5, so one thing is clear that if the power is higher, as a result the temperature generated on top of transistor will also be higher. Now, in this case the power is higher, sorry, in this case when increase the voltage, one thing is clear that we may understand, since I am increasing the voltage, the current flow will always decrease, right. So, consider, okay. So, when we calculate IE is equal to 0.5 divided by 0.1, so which is 5 amps, sorry, the current will be always higher, but the voltage drop will be decreased. But when you see the ratio, the amount of current flow is completely higher when compared to the voltage drop across your transistor. As a result, the power will be even higher. So, that is why increasing the voltage increases the current flow, even though the voltage drop across the transistor is decreasing, the multiplication factor of your current and voltage will be always higher, the power will be always higher. So, when we calculate the power at this point, so when we see the voltage drop across collector and emitter, it is 15 minus 0.5, which is 14.5. So, when we see the power 14.5 into 5 amps. So, it is somewhere around 72.5 watts approximately, right, 145, yeah. So, which means that when you see increase of 5 times, it is increasing drastically, almost equal to the 5 times, even though the voltage drop across is increasing. Imagine if it is of 1 volt. So, here the voltage drop will be 14 and the current will be 10, 140 watts. So, one thing it is clear that as we are keep on increasing the voltage, the current flow through the system is increasing, even though the voltage drop across the transistor is lower compared to when it is in low voltage input value, but the fraction of the multiplication fraction of voltage and current, which is nothing but the power, is really higher. Because of that, this 2N3055 will starts heating. So, in order to understand how much voltage, how much degree centigrade it will heat, you have to understand about the power dissipation factor, which you can get from data sheet. So, when we look into the power dissipation factor, so we will see how can we look into the power dissipation factor. Let me open the data sheet. So, when we see here, it is clear that watt per degree centigrade, it is 0.657. So, it is 0.657, 0.657 watt per degree centigrade, right. That means 0.657 watts is responsible for 1 degree. Now, we have a wattage of 14.9 watts. So, how many degrees it will be? 14.9 divided by 0.657. When you do, we can understand the value. So, let me calculate 14.9 divided by 0.657. So, approximately 22 degree, and when you see it is starting from 25, see this value is somewhere around 25 degree. Now, 22 plus 25, it will be somewhere around 47 degrees centigrade, right. So, because of 0.1, and is you know that the temperature, it is an energy, it changes with respect to the time. If you keep on apply the same voltage for a particular duration, the temperature will always range, but the factor at which it changes, it will be always smaller when compared to the fraction at which it changes when the input voltage is higher, right. So, but it starts heating, right. If you apply higher current, so that higher wattage, as a result higher current flow through that, higher current flow, higher wattage, higher power dissipation and higher temperature with a lesser time, right. And when we also see look into the data sheet of 2N3055, the maximum operating temperature of 2N3055 is 200 degrees centigrade. So, if it is more than 200 degrees centigrade, there are chances of damaging the circuit. So, in order to not to damage, so what we can do is that even in normal day to day life applications, if you see 2N3055 at power transistor, they will be always kept under heat sinks. The purpose of heat sink is, if the heat is higher, it will dissipate across, it will convect to the air. As a result, the average temperature will be smaller. So, it can operate for higher range. So, that is the whole idea, that is why we will always keep on the heat sink. So, when we look into circuit here, so this is our 2N3055. So, this is our 2N3055, and on top of it we have sticked LM35, which is a temperature sensor, which we have already discussed in the previous session, right. And this is the heat sink, the black color one, whatever you see is heat sink. So, if it is heating, automatically it dissipates to air, it will convert convection, convection will take place, and these are the connections, and this is being connected to the board. This is the board, right. So, we will come back to the board later on. Now, we will see other part. So, what we have seen, we understood about how exactly and what range of input voltage is being applied to the input plant, such that it will not damage our plant circuit. So, that means we require the input voltage maximum of 1 volt, not more than that, right. So, since when you look into the system, the manipulated variable value will be 1 volt. So, this 1 volt is not a generic for all the plants, this is particular to this plant. If you change the plant, if you know what range it can operate and what current like what is the maximum current it can withstand. So, based upon that you can tune these parameters, you can vary the output voltage. How can we do? By changing the parameters of a controller. So, in order to understand that, we will look into the controller too. So, now we will see the same working in the multisim. So, I will create a new circuit. Since this is not the first time we are using multisim, I do not want to explain anything. So, we will take op amp and we need a transistor. So, I will go with NPN transistor. Okay. So, this is 100 amp by amp. Okay. So, I will take one more resistor and I will take one more resistor here. Let me rotate. Connecting, and this is to be connected to the ground. Whereas, I need a power supply, I will go to the power supply, DC voltage, connect it here. So, since we are discussing about 15 volts, let me change it to 15, and this is 180 ohms. What about this value? This is 0.1 ohm. So, the wattage that we have taken was higher, which is of 10 watts. Now, okay, let me take this power transistor. This I am connecting it here, negative, connecting it here. Then this should be connected to a voltage source. Ground. So, the maximum voltage is 1 volt. Now, when I switch on, we can see the voltage drop. Oops. One thing is clear that at this particular terminal, so the voltage is 999.99 millivolt, almost equal to 1, that means both are at same voltage. So, since this is connected at the same point, I do not know why it is not showing, this should be also at the same value. Let me close and take a voltage. Okay, let me run. Okay, see, we can see 999.9, that means the voltage drop across this resistor is also 999.9. Now, what will be the current? So, since for simulation purpose I have used 10, 1 divided by 10, 0.1 amp, right, 0.1, approximately 100 milliamps. So, if I see the current flow here, the IC, and as we know that IC and IE is always close, and alpha times is the relation, and alpha is also 0.99, it is also close to 0.1 amps, right. Now, what I told you was, so this is 15 volts whatever we applied, and this is 1 volt. What about the rest of the voltage? So, the voltage drop. So, how do we calculate when you apply KVL? This is 15, this is 1. So, the voltage drop across this will be 14, right. As a result, the complete voltage drop will be at this point. Now, if I keep on change, if I decrease the input value, even the voltage drop across this will always decrease, the current flow will always increase, right, because it is divided by. When I see, sorry, the current will be always decreasing, right, 19. Now, what if I change the resistance value? So, we will go back to the 0.1 ohm resistance, and let me see, start from 0.1 volt, right, 0.1. What I will do is that I will take voltage and current, and I will keep it here. So, we can see both the voltage and current now. So, this is showing, yeah. So, 0.1 volt is the input we applied. So, 99.992 almost equal to 0.1 volt. So, the current is 1000 milliamps, meaning 1 amp of current, right, 0.1 by 0.1, 1 amp, I am increasing, I will say 0.2, right, see 2 amps of current, 0.5, 5 amps of current, see the voltage drop. So, this is also somewhere around 0.5, 499.98 is almost equal to 0.5 volts, 15 volts is input applied, 15 minus 0.5, 14.5 is the voltage drop across collector and emitter of the transistor. So, this current and the voltage drop across is responsible to generate heat. Since it is a simulation, we cannot see the heat, we can only understand about what is the current flow, what is the voltage drop. So, based upon the data sheet, based upon the parameter, the relation between the temperature and the wattage, we have to calculate what will be the power, what will be the temperature on top of the transistor. Now, I will change it to 1, right. When I change it to 1, the value is 936 milli, approximately equal to, let us say 0.9 volts, 0.93. So, close to 1 volt, this is 1 volt, this is 15. So, because of that we can see 10 amps, approximately of 10 amps of current is flowing through that, right. So, this is a way we can understand how exactly how much to be applied, so that the plant will always will be in a safe zone. So, in this case one thing is clear that the operating range, input voltage range is of 0 to 1, because the input to the system is only voltage. This is also called as voltage control current source, because voltage is changing based upon the input voltage, the current flow in the collector is completely changing. That is the reason it is also called voltage control current source. Now, what is the importance of having a 10 watt? When you recall what we have seen, when we recall our simulation, we have mentioned 10 watt. Why? The reason is the current flow maximum we are using it 10 amps, right. The voltage drop is 1. Your transistor should not damage, your resistor should not damage. So, in order to not to damage, it should, the capacity of your resistor should able to withstand for such a higher power. So, if you want to calculate the power dissipation, the power it can withstand, so which is nothing but 10 into 1, which is 10 watt. So, that is the reason we are using 10 wattage resistor, 0.1 ohm 10 watts resistor. If it is possible, try to go with even 20 watt, so that the withstanding capability, you cannot even see any kind of heat on the resistor at all. So, that is the reason we are using 0.1 ohm 10 watt resistor. So, depends upon the operating current and depends upon what is the voltage drop, you have to choose your resistor. So, if you go with a higher resistance value, and if you go with the 2N3055 with a high, other than 2N3055, if you have any other transistor which can withstand even higher current, the same plant can be used for higher current application, very fast temperature output applications too, right. So, one thing is clear that the working of op amp, working of heating circuit and making use of a transistor and op amp, how we are going to generate heat, and it is clear the input voltage is 0 to 1, such that the current, the maximum current it will be at safe zone, which is of 10 amps. Because of that, it generates heat, and that heat is being sensed by a sensor, right. Now, what we need? An automatic controller, we do not need a manual controller, meaning in a manual controller a human or some person has to be observe what is the heat of the system, and based upon that he has to take a call whether to switch on or whether to switch off or whether to change the input voltage such that it will maintain. And as long as human is involved into the system, it will be always, there will be always an errors. So, in order to avoid it, one way is going with an automatic controller. How can we design it? If you understand, we have discussed about our on off controller, right. So, if you see on off controller, the name itself says you that it will always switch on, switch off, switch on, switch off. And moreover, in our day to day life applications, if you see, the same type of controlling can be seen in refrigerator circuits. So, if you observe, when the temperature is decreased, the refrigerator will switch on. When the temperature is, when the temperature increases based upon the set point. So, in order to maintain to the set point, it will switch on the refrigerator. So, once the temperature is below the another threshold value, it will switch off. You can even hear, you can even hear when you are very close to the refrigerator, you can see tuck tuck sound kind of thing. It is nothing but the relay switching on and off of your power supply, right, on even iron box. So, when I say automatic iron boxes, that has a bimetallic strip which acts as an actuator. So, when the temperature is, so if you understand about the bimetallic strip, it is made up of two dissimilar metals joined together. So, that because of different properties of two different materials, the expansion coefficient will be completely different from different materials. Because of that expansion, it will causing it to bend to one direction. As a result, the switch will be on or off. So, such kind of actuating system can also be used, which acts as an on off controller in such case of applications. So, to switch on or switch off your system. So, if you want to understand very in deep about the circuit, we can see that. So, a mechanical system, if you can see that, if I have a tank and if this valve is connected to the float, right. So, as long as this particular tank is filling, right, till it reaches to this particular level, right, the float will causing it to move upwards. So, causes the circuit to break. As a result, no power, since it is a solenoid switch, there is no power. So, no input to the tank. Now, when the level is decreased below this value, so the float will come down. So, again the circuit will be on. So, it will try to maintain within this particular range. So, in order to even much more understanding about the system, we can see that if I say this is my set point, so consider this is 50 degree, right. In case of hysteresis or on off controller, you will always have to set two thresholds, right. So, let us say this is 55 and this is 45. If your input voltages keep on increasing more than your 55 degrees centigrade, right. So, a controller, so this is your higher threshold point, this is your lower threshold point. If the input voltage is greater than the higher threshold point, as a result the controller output will be off. Now, again it will switch on only when the input voltage is lower than the lower threshold value. So, it will always fluctuate between these two thresholds. Moreover, when you see the output across the controller, it will be always on for some time, depends upon the system parameters, off, again on, off, right. So, such kind of operation we can see on off kind of thing in our circuit. So, how do we design? So, the idea is that how do we design an on off controller using an operational amplifier, right. So, this is an inverting type of on off controller, or also called as Schmitt trigger. If you recall, we have already discussed about on off controllers or Schmitt triggers in our previous session. So, it is also similar to that, right. So, since it is inverting type, when the input is positive, we will get a negative, right, we will get a negative output, that is clear. Now, how do we set our thresholds? So, when we recall, we have to set two thresholds, one is here higher threshold point, other one is a lower threshold point. How do we set? That will be completely done by choosing these resistors. So, in order to understand, okay, in order to understand how exactly it works, so just simply apply KCL, right. We can see that when you apply KCL, I1 is equal to I2 plus I3, right, and if I say this is V1, right. So, what is I1? So, we can say V plus minus V1 by I2, which is nothing but V1 by R1, and I3 is nothing but V1 minus V0. In this case, I am saying it as V1 as V0 divided by R3. So, when we calculate the things, so we can rewrite V1 as R equivalent by R3 into V1 plus R equivalent by R1 into V plus. So, where R equivalent is nothing but R1 parallel to R2 parallel to R3. We can try, we can solve it. When you solve this, just solve the previous equation. So, take all V1s to one direction and remainings to the other direction. So, we will get, and we are saying R equivalent is nothing but R1 parallel to R2 parallel to R3. When we do that, we will get V1 as R equivalent by R3 into V1 and R equivalent by R1 into V plus. That means, it is clear that it depends completely upon our V plus, and it also depends completely upon VO1. Now, how does VO1 works? So, we know that one if the input voltage, if this particular voltage is higher than this value, this will be minus VCC, right. So, recall our Schmitt trigger, right. If the input voltage is greater than higher threshold value, it goes to minus VCC, and if the input voltage, in this case since it is a negative, if the input voltage is lower than the lower threshold, it goes to plus VCC, right. It is a reverse of your non-inverting type. So, sometimes we will get plus VCC, sometimes we will get minus VCC. So, if I rewrite this, we can rewrite it as R equivalent by R3 into, sometimes it is V plus R equivalent by R1 into V plus, and sometimes it will be, this is one threshold, other threshold will be minus R equivalent by R3 into V plus R equivalent by R1 into V plus, because this V plus is fixed. So, V plus is nothing but the plus VCC and minus VCC in this case, right. So, VO1 is nothing but, sometimes it will be plus VCC, which is nothing but V plus, in this case we are saying, and sometimes it will be minus VCC. So, these are the two thresholds. So, when I rewrite, the thresholds will be V 1 is equal to R equivalent divided by R 3 into V plus V plus into R equivalent by R 1, and other threshold is nothing but minus R equivalent by R 3 into V plus, or we can say V minus 2, V minus is nothing but minus V plus V plus into R equivalent by R 1. So, how do we calculate R equivalent? When we see, we know that R 1 and R 2, R 3 values are 100, 180, R 3. So, when we calculate R equivalent value, so 1 by okay, I can say 1 by R equivalent is equal to 1 by 180 plus 1 by 100 plus 1 by 100. So, first what I will do is that I will calculate for these two R 1 and R 2, it will be 50 K. When resistors are same, if those two are in parallel, it will be R by 2. So, it is 50 K. Now, 1 by 50 plus 1 by 180. So, let me solve it. Windows are 1 divided by 180 plus 1 divided by 50. So, it is 0.255. So, 1 divided by answer. So, we will select 1 by x. So, that is nothing but 39.13. So, R equivalent is 39.13. Okay. One more thing is, this is 50 K, this is ohm. So, whatever the calculation we made is wrong. So, let me do once again, 1 by 100 1 2 3 plus 1 divided by 100 1 2 3. So, 1 by x. So, this is 50 K. So, 1 by 50 K. Now, we need 1 divided by 180 plus 1 divided by 50 K, 1 2 3. So, it is 0.0055. So, answer inverse will be R equivalent 179.35, approximately equal to 180 ohms. So, R equivalent is 180 ohms. Now, we need to find out V 1 and V 2 thresholds. Let me erase it. So, we understood R equivalent value, which is 180 ohms. So, one threshold V 1 180 divided by 100 K into 15, let us take I am applying, plus 180 divided by R 1, R 1 is 180 into 15. So, 180 cancel. So, 180 by 100 K, 18 by 100. So, 1.8 into 15 milli plus 15. So, when I see the value 1.8 into 15 into 0.001, it is milli plus 15. So, one threshold is 15.027. What about the other one? V 2. So, minus 1.8 into 15 milli plus 15. So, this will be (15 minus 1.8 into 0.015, 15 milli. So, which is 14.973. So, these are the two thresholds in this case. So, when we recall, one threshold is 15.027 and the other threshold is 14.973. So, since it is an inverting type of Schmidt trigger, when the input voltage that means if the input value is greater than 15.027, the output will be on, right, and when the input is lower than 14.93, the output will be off, reverse to this value. Now, so how do we understand in terms of degree centigrade? So, if you want to understand, we have to understand what is the sensitivity factor that we have used as an input, as a set point to the system. So, that we understand, we can do that, but this is not the final output. So, in order to understand, we should understand what is the signal conditioning circuit that we are using it here, right. So, now if you see the output of a controller is somewhere around 15 volts, but is 15 volts is good enough for our op amp or for the plant to withstand? No, because when you apply 15 volts as an input to the plant, if you recall, apply 15 volts here. So, here the voltage drop will be 15 volts, so the current flow will be 150 amps. That is not we required. That is also any generation of 150 amps is really difficult. Your power source cannot generate such a higher current. So, that is the reason, since our operating range of the plant is somewhere around 1 volt. So, we have to convert 15 volts to 1 volt. Output of the plant is 15 plus 15 or minus 15. So, how do we do that? So, in order to do that, we are using a signal conditioning unit here, this signal conditioning unit. If you recall, if you remember, how do we set a gain for an inverting or non-inverting amplifier? The gain of your system, inverting amplifier, if I see the gain of an inverting system, if I say V naught by V1 in this case, entirely depends upon your feedback resistor divided by input resistor, which is nothing but R5. So, if you want to use it as an amplifier, the R6 resistance value should be higher than the R5 resistance value. As a result, we will get a higher value, but in this case we need to attenuate. The reason is the plant can only withstand with a maximum value of 1 volt, and since 15 is the maximum voltage that we are getting, right. So, that means 15 volts has to be converted to the 1 volt. How do we do that? In order to do that, we have to use an attenuator. So, in this case the gain of the system should be 1 by 15. So, if I take gain of 1 by 15 and multiplied with the input voltage of V01, so the V naught will be always 1, right. So, the combination of on off controller and the signal conditioning circuit is the output of the signal conditioning circuit is the input of the plant. So, that whole combination is our controller in this case. I hope you understand why we have used a signal conditioning circuit at the output of on off controller, right. So, we have to design in order to match the input parameters of the plant with respect to the controller output. So, we need to have one more block, right. So, that block is a signal conditioning block in this case. Now, what is the use of having these two resistors? When you recall the characteristics of an op amp, we can see that the input bias currents and input offset currents, right, which changes the output voltage even though when you do not apply any input voltage, right. So, in order to eliminate the effects due to the bias currents, right. So, rather than simply connecting positive terminal to ground, if you connect an R compensation resistor at the positive terminal of an op amp, the effect due to the bias currents can be eliminated. So, what R comp resistor should be? The parallel combination of feedback resistor and input resistor, that is the reason. So, one input resistance and the other one is feedback resistance. Now, this is a pot, so that we can vary. So, if I say 15%, so 15% of 100 kilo is nothing but 15 kilo and this is 1 kilo. So, 1 kilo by 15 kilo, which is nothing but 1 by 15. So, even if I want to increase or decrease, by using this we can do, or you can replace this with simply 15. So, why we have used a pot? Because even in case if the plus VCC and minus VCC is changing, the same circuit should be responsible, or the same circuit should be used even to generate the required output voltage. That is the reason by simply using a pot, we can, even the input voltages are changed, by tuning the R5 resistance value, we can achieve the required output voltage. So, that is the requirement of a signal conditioning circuit in this case. Let us see whether our signal conditioning circuit, theoretically whatever we have seen, our signal conditioning as well as the on off controller, whatever we have designed as per our requirement, is working perfectly or not. So, before looking into the experimental, we will see the simulation version and we will understand. Okay. So, sorry. So, let me save this. So, the name I am saying it as heating plant. Okay. Let me open a new file. So, I need an op amp. So, I am taking an op amp, positive, negative. I need 3 resistors. So, this is R1. So, R1 180 ohms, 180 ohms, and R2 100K, So, right, and R3, the resistance value is 100K. So, this is the input, negative terminal is the input in this case. So, we need to connect ground. Okay. Since you do not have a power supply, what I do is I will take an op amp with a 5 terminal. So, even we can connect plus VCC and minus VCC here, and this is my error input. So, that will be passed through a triangular voltage, triangular generator. So, easy for us to understand when it is switching on and switching off. Sorry. So, the voltage should be, let us say 20 is the maximum voltage amplitude, because the thresholds are 15 point something and 14 point something, right, the lower and higher. So, input voltage should be always greater than that, right. So, plus VCC and minus VCC should be connected. So, what I will use, I will take a DC voltage. So, rotate it. So, plan to use 15. So, what I will do is this I will change it to 15, right. Now, this should be connected to the ground. I will take a ground, connect it here. I need another voltage source because for negative terminal, negative voltage, and the value should be of 15, and other terminal should be connected to ground. Another voltage source which should be of same V plus, oh sorry, not this, DC voltage, let me rotate, this should be. So, this is very much important what voltage we are using, because when you see the threshold values, it depends upon what is the supply voltage that we are connecting as well as what is the voltage that we are connecting at this point. So, since we have calculated for 15, let me change it to 15, and other terminal should be connected to, right. So, now we have to understand this. So, the circuit is ready, only thing is we have to do the simulation. Before doing simulation, let me connect voltage sources, sorry, voltage probes at output as well as input. Okay, let me change the input to some sign, AC voltage. So, peak value is somewhere around 20. Okay. Now, if I zoom the system, okay. So, let me go to the grapher. So, how do we understand this? So, let me make it a single, right. So, this is the input, the green is corresponds to the input, the blue is output. So, one thing we can see that it is always fluctuating, but whether it is fluctuating at the same time. So, to understand, let me take two cursors. So, one is y axis cursor. So, one value is somewhere around 15 point something. So, if we calculate, so the value is 15 plus 0.027, 15.27, other one is 15 minus 0.027, which is 14.97. Yeah. So, one is 15.27. So, when I see C1 cursor, so the cursor 1 is somewhere around 15.6. So, I have to keep it as 15.0. Okay, I can keep it at 15.0. Let me keep it at 15.066 approximately, and the other cursor should be somewhere around 14.97. Let me try whether I can get or not. Yes, 14.98, right. Now, if the input is greater than this point, so it is almost looking same. So, what I will do is that I will change what I will do here, rather than saying peak value, peak of 20, I will say offset of 10, peak of 10. Okay. This is good for us. So, when we look into the grapher, so what I will do is I will zoom it. So, the maximum 25 and the minimum, let us take it as 5. So, 14 point cursor to 14.097, yeah, and other one is 15.0273. So, when the input is greater than C1 higher threshold, we can see it is going to switch off. Again when the input is lower than the C2 threshold, right, at this point, somewhere around this point, it started going to the other state. So, that is clear that as long as input is greater than the higher threshold value or even higher than the lower threshold value, it will be always in the off state, right, and when the input is lower than that particular value, then it is on. So, that is what even we require, right. So, when do we have to switch on? When the temperature is lower than the lower threshold value, then it has to switch on. So, observe the temperature is lower than. So, if I say the green color one is the temperature, it is increasing, and at this point since it is on, it is off. So, so no power. Since there is no power, it will start cooling because of the convection, or if you have any forced convection, that is also fine. So, it will be starts cooling. When it is lower than the lower threshold value, then it starts. That means it starts pumping current. As a result, it starts heating. So, the duty cycle or the frequency at which it switch on or switch off entirely depends upon the rate at which depends upon your input, how it is heating your plant, right. So, this way we can understand how exactly the Schmidt trigger can be designed based upon the requirement. Now, when you see the thresholds are closely selected such a way that it should always on and off at very smaller ranges. The reason is that in some of the biomedical applications, we require to constantly maintain the temperature of the plant to be plus or minus 0.1 degree or 0.05 degree variation in the temperature. So, in such a cases, such a close thresholds are very much important. Moreover, one thing we have to understand, since the controller is making your system to on off at a regular intervals of time, the withstanding capability of your system, if your system cannot withstand for such an fluctuations in your input voltages, it may also damage your system. So, that is very much important. So, we have to see understand whether the system operating range as well as the capability of a system when there is input keep on fluctuating. As long as that is satisfying, there is no problem. But another problem is that when you observe the diagram what we have seen, right. So, these are your two thresholds, your output always fluctuate between these two ranges, right, higher threshold and lower threshold. As long as these two thresholds, this range is okay, we can go with a on off controller. So, it is clear that on off controller is not controlling it, it is on and off, on and off. So, depends upon variation in your input based upon the set point, but sometimes for some particular systems we require to maintain the temperature to be always same, always set as per your input set point. Let us say 50, it should always maintain at 50, and the system should not switch on and switch off, it should always power, it should be always in on condition, but the variation input voltage should be always changing. In such a cases, if we want to design, so we have to go with the other kind of controllers. So, those controllers are our P controller and PI controller and PID controller. How complex you make? So, how complex you make entirely depends upon how many number of proportionality or how many number of what do you call different kinds of controlling mechanisms that you are using. If you are using a proportional controller, it is a simple proportional controller. If you want to make it complex, if you want to have a more response, very good response, very less error and very accurate, then we have to go with a higher complex system, those are PI and PID controllers. So, we will see how exactly the P controller will work and how exactly the PI controller will work in the next module. Thank you.